Hello, everyone, and welcome to today's webinar, Far Field Optical Nanothermometry via Individual Luminescent Nanoparticles. I am Antonina Salcedo of LabRoots, and I will be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Andor. To learn more, visit andor.oxinst.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you have trouble seeing or hearing the presentation. This webinar is educational and thus offers free continuing education credits. Please click on the Continuing Education window at the bottom of your screen to obtain your credits. I'd like to now welcome our speaker, Andrea Pickel, Assistant Professor at the Department of Mechanical Engineering at the University of Rochester. Andrea, you may now begin your presentation.
Well, thank you for the introduction. So once again, my name is Andrea Pickel, and I'm an assistant professor in the Department of Mechanical Engineering at the University of Rochester. One area that my research group really focuses on is developing new techniques to measure temperature at the nanoscale. And in particular, a lot of our work focuses on using individual luminescent nanoparticles to measure temperature at the nanoscale. And so that's the work that I will be talking about today. All right, so I'll begin by talking about some of the reasons why we need nanoscale thermometry. And so one reason that we're probably all familiar with is that our electronic devices, things like laptops and smartphones, are very prone to overheating. And we experience that in a macroscopic sense in our everyday life. But the origins of these problems are really at the nanoscale. And that's because transistors now have feature sizes on the order of tens of nanometers. And so hotspots have shrunk to the nanoscale as well. Another area where heat transfer is important is in a number of energy applications. And here, one particularly important example is lighting, which accounts for about 6% of our total energy use here in the US. And as we've shifted away from incandescent light bulbs to LEDs, the thermal challenges associated with lighting have shifted to the nanoscale. And that's because LEDs are semiconductor devices that contain many thin layers, some of which are only a few nanometers thick. And although LEDs are a lot more efficient than incandescent bulbs, they still waste typically at least 10% of their input energy as heat. And an LED operating above its maximum rated temperature can suffer huge performance and reliability losses. Even a 10-degree increase can cut the lifetime of an LED in half. On the other hand, there are also applications where rather than being parasitic, localized heating can actually be desirable if it's carefully controlled. One example here is thermal cancer therapies, where nanoparticles are embedded in cancerous cells, and then a laser is used to selectively heat the nanoparticles with the goal of then killing the cancerous cells by heating them while leaving the healthy tissue intact. Another place where controlled localized heating can be beneficial is in some next-generation data storage technologies. One example here is heat-assisted magnetic recording, where localized heating is used to temporarily change the magnetic properties of the recording medium. And another example is phase change memory, where joule heating is used to switch a nanoscale amount of a phase change material between two different states. And so next, to understand how specifically the inability to measure temperature limits some of these technologies, I'll discuss a couple examples in more detail. Heat-assisted magnetic recording, or HAMR, is, as I said, a next-generation hard drive technology, and it's expected to more than double storage densities. The key idea behind HAMR is to plasmonically excite this gold lollipop-shaped structure known as the near-field transducer, and then couple energy from the 30-nanometer peg across a nanoscale gap and into the recording medium below. And this energy then locally heats the recording medium, which temporarily lowers its coercivity and ultimately allows for smaller bit size and higher storage densities. But one challenge for HAMR is that it's known that rather than heating the recording medium, instead significant overheating of the 30 nanometer PEG can occur. And degradation of this PEG can cause entire HAMR drives to fail. And so again, it's thought that the cause of this degradation is overheating. But right now, there's no existing technique that can measure the temperature of the HAMR PEG during operation to verify whether this is actually the case. Phase change memory is another next generation data storage technology. And here the idea is to use Joule heating to switch a nanoscale amount of a phase change material, typically a chalcogenide glass, between a resistive amorphous state and a conductive crystalline state. And the way that this works is that to go from crystalline to amorphous, the phase change material is heated above its melting temperature and then quickly quenched to lock in the amorphous state. And to go from amorphous to crystalline, the phase change material is heated above what's known as the crystallization temperature, which is lower than the melting temperature, and then held there until it recrystallizes. It's known that the crystallization temperature of these nanoscale amounts of phase change material can differ significantly from the bulk value. Some estimates suggest by hundreds of degrees. But again, right now, there's no existing technique that can measure this nanoscale crystallization temperature in phase change memory devices. So stepping back for a minute and starting to think a bit more broadly about these examples that I've just discussed, there are certain recurring themes that start to emerge in terms of the types of systems where we'd like to be able to measure temperature at the nanoscale. And so one theme is that we'd like to be able to measure the temperature across stacks of thin films, whether that's in the active region of LEDs or other optoelectronic devices, or in the recording medium and heat sink layers underneath the HAMR PEG. Another theme is that we'd like to be able to measure the temperature of nanoscale hotspots, like the HAMR PEG itself, or the unknown crystallization temperature in these phase change memory devices. And so today I'll focus on the nanoscale hotspot, since that's really the particular application that the technique I'll be talking about today is best suited to address. Before getting into some of the experimental techniques, I wanted to discuss some of the more fundamental motivation for nanoscale thermometry techniques. And what I mean by that is we might ask, couldn't we just develop very sophisticated models or calculations in order to determine what the temperature of these nanoscale hotspots could be? And it turns out that one major challenge here is that the classical laws of heat transfer that, say, you might learn in an undergraduate course don't always hold up at the nanoscale. And we can understand that by thinking about the example of a heat-generating sphere in an infinite medium. So if we zoom into this medium, what we'd see is that there are heat carriers, say phonons, that are running around and colliding with one another. And in between collisions, they travel an average distance that we call the mean free path, or lambda. And in the classical Fourier's law case that, again, you might see in an undergraduate course, the diameter d of the sphere is much larger than the mean free path lambda of these heat carriers. And so we can then use this kinetic theory expression for thermal conductivity K that says K equals 1/3 CV lambda. And we can use this expression along with Fourier's law to calculate the temperature rise of the sphere. But now let's consider a different case where we have a heat-generating nanosphere whose diameter d is much, much smaller than that mean free path lambda. It turns out that in this case, which we call a ballistic heat transfer scenario, Fourier's law no longer applies, and instead we have to solve the Boltzmann transport equation in order to calculate the temperature rise of our sphere. And in this simple case, we can get an analytical solution, and it turns out that when the sphere is much smaller than that mean free path lambda, the temperature rise is much, much larger than what Fourier's law predicts. And so we can expect that in other more complicated nanoscale geometries and devices, we're again going to have deviations from this classical Fourier heat transfer scenario, but we don't always know the details. And so we really need experimental tools in order to characterize and understand these kinds of nanoscale subcontinuum effects. Starting to think in more detail about thermometry methods that already exist, we can divide them into two broad categories, the first of which is non-contact optical methods. And here, one example that may be quite familiar is infrared thermal imaging. And this is a very convenient approach, but the spatial resolution of this kind of technique is limited to about 10 microns near room temperature due to the long wavelengths of thermal radiation. And you can do a bit better by going to high temperatures, which is something that I've done along with some collaborators previously. But even at 3000 Kelvin, your spatial resolution is still limited to about a micron. And so you just cannot get the resolution that you need in order to measure nanoscale hotspots. There are also many laser-based techniques. One common example here is thermoreflectance techniques that use the temperature-dependent optical reflectivity of a thin metal transducer layer for thermometry. And here you can get spatial resolution down to a few hundred nanometers, but that's a very fundamental limit due to optical diffraction. And so to get the spatial resolution that we need to measure nanoscale hotspots, we might instead think about contact-based techniques. For example, scanning probe techniques that essentially use a modified AFM tip as a nanoscale thermocouple. And here you can get quite good spatial resolution, but the challenge is that the probe can act as a parasitic heat sink and introduce unknown thermal contact resistances. And so it can be very difficult to accurately extract the true temperature of the sample that you're measuring. That said, as convenient as the non-contact techniques are, they are fundamentally diffraction limited, as I mentioned. And so the question that we like to ask in my group is there some way that we can still use far-field optics, but somehow beat the diffraction limit in order to measure the temperature of nanoscale hotspots? And so there's a number of ways that we try to do that. And one possibility, and the one that I'll focus on today, is that of using a single nanoparticle with temperature-dependent luminescence in order to measure the temperature of these nanoscale hotspots. The basic idea is that we take a single nanoparticle, we place it on some sample of interest, we use a laser to excite the nanoparticle, and then we measure the temperature-dependent luminescence emitted by the nanoparticle in order to determine the temperature of our sample. And the idea here is that the nanoparticle is very small and in excellent thermal contact with the sample such that it accurately reports the true temperature of the sample. And now I just want to drill in for a moment on how we're getting nanoscale temperature information, even though we're using a diffraction limited laser. And so it's true that the diameter of our excitation laser beam is indeed diffraction limited. But the key is that if we are only exciting a single nanoparticle, then we know that the temperature information comes only from the nanoparticle luminescence, and therefore the spatial resolution of the temperature measurement is governed by our nanoparticle size rather than the diffraction limited laser spot. And so when we perform our experiments, we ensure that the nanoparticles are spaced sufficiently far apart on average, such that their diffraction limited emission spots don't overlap. And so what that means is that we can't map temperature with this approach, but we can get really excellent single point temperature measurements. And that's exactly what we need for these nanoscale hotspot applications. And so going forward, I'll talk about the specific nanoparticles that we use, the thermometry signals that we've applied, and finally, how we're able to place a single nanoparticle at the exact location where we want to measure the temperature. And these are all important steps towards actually measuring the temperature of one of these nanoscale hotspots, like the hammer peg, which was the motivating application for much of this work. So next, I'll talk about the specific type of nanoparticles that we use and how we perform our temperature measurements. We work with what are known as upconverting nanoparticles, and there are many different types, but they all typically consist of a fluoride or an oxide host matrix doped with a combination of lanthanide ions. The canonical upconverting nanoparticle composition, and the one that we use quite frequently, is a sodium yttrium fluoride host doped with a combination of ytterbium and erbium ions. They're called upconverting because the sensitizer ions, which in this case is the ytterbium, absorbs two low energy near infrared photons, transfers this energy to the erbium, which finally emits a single photon in the visible wavelength range. And these upconverting nanoparticles, or UCNPs, have a lot of advantages that make them popular for a variety of imaging and sensing applications. One advantage is that they're extremely photostable, so they don't photo-bleach or blink. Bleaching and blinking are big problems for some probes like quantum dots, so UCNPs are an appealing alternative. UCNPs are also easy to synthesize using high-throughput combinatorial methods. They're also highly tunable, so just by swapping out one dopant for another or changing the dopant concentration, you can get a big variation in parameters like emission wavelengths. And finally, UCNPs are highly biocompatible, in part because many of them are excited in the first or second biological windows, which are regions where tissue is relatively transparent. And so for this reason, the bioimaging community has led a lot of their development. But the reason that we're interested in UCNPs is that they have a particular temperature-dependent emission feature. So as I mentioned a moment ago, the upconversion process begins when the ytterbium absorbs two near-infrared photons and then transfers this energy to the erbium. Next, the erbium decays non-radiatively to a lower energy excited state before returning to the ground state by emitting a single green photon. This is clearly a complicated system with many different energy levels and transitions. But we can really understand the basic temperature-dependent physics by considering a simple three-level diagram for erbium. So what you see here is erbium's ground state along with two higher energy thermally coupled excited states from which the erbium can return to the ground state by emitting a green photon. And the key is that the relative population of these two excited states is governed by Boltzmann statistics. And that's fundamentally where our temperature-dependent signal comes from. The relative populations of these two excited states, it turns out, are directly related to the emission intensities from the two corresponding transitions. And we can see that by looking at single particle spectra taken at different temperatures. So if we divide the emission wavelength range into two bands, lambda 1 to lambda 2 and lambda 2 to lambda 3, we see that when we increase the temperature, the emission intensity from this first wavelength band, which corresponds to the transition from the higher energy excited state to the ground state, increases relative to the emission intensity from the second band, which corresponds to the transition from the lower energy excited state to the ground state. We can then define a temperature-dependent ratio as the integrated emission intensity from the first wavelength band divided by the integrated intensity from the second band. And this is an approach known as ratiometric thermometry. It's been used quite commonly for ensembles or large groups of these upconverting nanoparticles, but prior to our work, single nanoparticle measurements were quite rare, and there were none that used single particles under 50 nanometers. Next, I'll just discuss briefly how we perform these measurements and then show some of the results. So we perform these measurements using a custom scanning confocal microscopy system. And we began by focusing a near-infrared laser using a high NA objective. And this focused laser beam then excites a single nanoparticle, which sits on both a piezo-controlled nanopositioning stage and a temperature-controlled thermal stage. We then collect the emitted luminescence, filter out any residual excitation light, and then we can send that emitted luminescence either to an avalanche photodiode for imaging or to a spectrometer with a CCD camera. And so here's an image of a microscopy system that we constructed here in my lab at the University of Rochester. This plot shows the ratio as a function of temperature for 5 individual 20 by 40 nanometer particles, which were confirmed to be single particles using SEM imaging. We can see that the temperature sensitivity of this technique is quite good, about 1500 ppm per Kelvin. And there's also excellent particle-to-particle uniformity, which you can see from the nearly overlapping calibration curves for 5 different particles. And just for perspective, again, this was the first time that particles below 50 nanometers had been used for thermometry. And this is about 20x smaller than the previously smallest single particles that had been used for isolated single particle measurements like we're doing, and about 5x smaller than the smallest single particle measurements for a particle that was attached to an AFM tip. And so this really represents a significant improvement in terms of the spatial resolution of this technique. All right, so next I'll talk about what began as an effort to answer the common and important question of whether our excitation laser could be heating the nanoparticle, but it ultimately morphed into a more complicated story that led us to uncover some important effects that occur when you excite these nanoparticles at very high excitation intensities, which has some important practical impacts in terms of this thermometry technique. So if we look at the literature data for nanoparticle ensembles, it's been shown that this temperature-dependent ratio is essentially independent of excitation intensity. But because single nanoparticle measurements are, as I said, much more rare, there haven't been the same kinds of systematic studies looking at how the ratio varies with intensity. But if we look at the typical excitation intensities required for single nanoparticles versus ensembles, we see that they're quite different. So specifically, single nanoparticles require much higher excitation intensities by several orders of magnitude. And so it's then natural to ask, could these high excitation intensities required for single nanoparticles affect this ratiometric thermometry signal? And here I want to discuss 2 different possibilities. So one possibility is that the high excitation intensity could increase the temperature of the nanoparticle, which is what we refer to as self-heating. The second possibility is that the high excitation intensity could distort the Boltzmann population distribution that our ratiometric thermometry technique relies on, even though the nanoparticle temperature hasn't changed. And so the second case seemed unlikely based on the precedent in the literature. And so we began by looking into this first case to see if the high laser excitation intensities could be heating the nanoparticle. And so we begin by first making what I call a worst case scenario estimate. So in other words, an estimate of the highest possible temperature rise that we could expect for our nanoparticle. And I'll illustrate that by building up a thermal circuit here. So we start by assuming that all of the laser light absorbed by the nanoparticle is converted to heat, although in reality, a small amount is upconverted to higher energy light. And we calculate the absorption cross-section based on the well-known cross-section for ytterbium ions, which are the primary absorbers of the 980 nanometer excitation light. And then this heat can either be dissipated on the air side, which we represent, shown here is the substrate side. So on the substrate side, we represent that with 2 different thermal resistors, one representing the thermal contact resistance between the nanoparticle and the substrate, and then another resistor representing the substrate thermal resistance. And then our other parallel path is that heat could be dissipated on the air side, which we represent with this thermal resistor R air. So again, we want the worst case scenario, the highest possible temperature rise that we could expect for this nanoparticle. And so to get that, what we do is we ignore the substrate side thermal resistors and we only consider R air. And so this isn't necessarily the most realistic scenario. In fact, based on our estimates of the magnitudes of these resistors, we expect that a lot of the heat actually will flow through the substrate side. But it is the most conservative. The reason for that is that R air is the largest thermal resistor, And so if we only allow the heat to flow out of the particle through the air, that will give us the highest possible temperature rise we could expect. And so for a 50 nanometer particle, which corresponds to those that we use in this next set of experiments, we calculate a value of about 2 times 10 to the 9 kelvins per watt for our air. And I'll refer to this value as our model from here on out. And for an excitation intensity of 3 times 10 to the 5 watts per centimeter squared, which corresponds to the upper end of the range that we use in this next set of experiments, we calculate a temperature rise of about 2.1 Kelvin. So not too bad, even in this worst case scenario estimate, we're only getting a few Kelvin temperature rise. And finally, just to familiarize you with the format that I'll be using repeatedly in this next section, here you see the temperature rise as a function of excitation intensity, and the slope of this line is directly related to the thermal resistance. And the y-axis here goes up to 50 Kelvin, just to emphasize that if we're interested in measuring temperature changes on that order, then even this worst case scenario, 2 Kelvin self-heating isn't a total deal breaker. However, when we actually started performing experiments where we measured the ratio of excitation intensity, we saw something that was different than what we expected. So here you see the ratio measured as a function of excitation intensity, where our substrate temperature is fixed at room temperature, about 296 Kelvin. And we see that as we increase the excitation intensity, that temperature-dependent ratio also increases. Likewise, if we park our thermal stage at a higher temperature of 350 Kelvin, and we again increase the excitation ratio, the excitation intensity, we once again see that this temperature-dependent ratio increases. So what we can then do is to convert this change in the ratio with excitation intensity to an apparent temperature rise. And if we do that, we get an apparent temperature rise of over 50 Kelvin. So much, much higher than our worst case scenario estimate of just 2 Kelvin. And from this data, we can also extract an apparent thermal resistance. And when we do that, we get a value of about 6.3 times 10 to the 10 kelvins per watt. So again, more than an order of magnitude higher than the worst case scenario modeled value. And so it was really this dramatic discrepancy between model and experiment that motivated the next set of experiments we performed to try and answer the question of, could the nanoparticle really be heating? And if so, how could we explain this? So after observing this unexpectedly large apparent temperature rise, one of our first thoughts was to next try to use a second thermometry method to verify this large temperature rise. And so for the sake of time, I won't go into details, but we developed a second thermometry method based on the temperature-dependent luminescence lifetime of these nanoparticles. And so we use this method to once again measure the apparent temperature rise as a function of excitation intensity. And once again, we got a quite large apparent temperature rise of somewhere around 50 Kelvin. And so the second thermometry method seemed to confirm that the nanoparticle was perhaps heating up by far more than our conservative model would have suggested. And we can also extract an apparent thermal resistance from the lifetime thermometry method, and it's similar to the value that we got from our original ratiometric thermometry measurements. Now, one thing that these two experiments both have in common is that the only parameter we're varying is the excitation intensity. And there are scenarios we can imagine, for example, if we were really off in terms of our estimate of the absorption cross-section, where the temperature rise that we estimate would also be quite off. But even if our estimates for the magnitude of the temperature rise were totally incorrect, if we started somehow changing the thermal resistors, so somehow manipulating the thermal environment surrounding the nanoparticle, this would have to have a noticeable impact on any true temperature rise. And so that's what we did next. We started by repeating our measurements on 3 different IR transparent substrates with thermal conductivity spanning over 2 orders of magnitude, namely a polymer, glass, and sapphire substrates. And when we did that, we measured a essentially identical apparent temperature rise in all three cases. And so that told us that the substrate thermal resistance did not seem to affect the heat dissipation. Now, if you recall, we actually thought that we should expect a lot of heat to be dissipated through the substrate side. And so next we decided to try varying the contact resistance to see if a large thermal contact resistance between the nanoparticle and the substrate could be limiting the heat dissipation. All right, so to vary the thermal contact resistances, we applied 5 different coatings to our samples designed to improve the thermal coupling between the nanoparticle and the substrate. So these coatings were spin-coated and drop-cast polystyrene. We applied HSQ, which is a spin-on glass, sputtered SiO2, and finally atomic layer deposition of SiO2. The ALD in particular ensures highly conformal deposition since it uses gas phase precursors. Nonetheless, we measured essentially the same apparent temperature rise for all these coatings. And so we concluded that the contact resistance does not impact the heat dissipation. And now it turns out that if you think a bit more carefully, changing the contact resistance is a little bit complicated because doing so actually changes the air thermal resistance as well. And so I won't go into all the details for the sake of time, but by taking that into consideration, we were able to conclude that none of the thermal resistors affected the heat dissipation. So the last thing that we tried is that we tried changing the absorption cross-section of our nanoparticles. And so we chose to do that by varying the nanoparticle size while keeping the concentration of the ytterbium ions constant, but with a larger size nanoparticle, you get more ytterbium ions and you increase the absorption cross-section. So what we found is that for both a 20 by 40 nanometer particle and a 50 nanometer particle, we measured, again, the same apparent temperature rise. And this just cannot be explained by any heat transfer model. The reason for that is that the temperature rise is equal to the heat absorbed Q times the thermal resistance R. We know that Q scales with the nanoparticle diameter D cubed. And so to have the temperature rise theta be independent of D, the thermal resistance R would have to scale as 1 over D cubed. And so it turns out that we're right in the middle of right on the border of being in a classical Fourier heat transfer regime versus a ballistic heat transfer regime, going to something I mentioned at the beginning of this seminar. But in either case, we can't get that 1 over D cubed scaling. We might be somewhere between the 1 over D scaling from the Fourier case or 1 over D squared from the ballistic case. But there's just no way that we can get that 1 over D cubed scaling. And so we concluded that the absorption cross-section and the particle diameter don't affect the heat dissipation. So just to recap what I've shown up to this point, first, our worst case scenario self-heating estimate predicted no more than a few Kelvin of heating. And then we found that the apparent self-heating that we measured, despite being 50 Kelvin or more, didn't seem to depend on any thermal parameters. So we tried varying all these resistors and the absorption cross-section, but saw no changes. And so at that point, we really had to ask, is there any way that this effect could in fact be non-thermal? And even though this had not seemed like a strong possibility early on, at this point, our experiments clearly said that this could not be a true temperature rise. And so my collaborators did some more modeling to really investigate in more detail what might be going on. So I'm fortunate to have some great collaborators, Dr. Emery Chan at Lawrence Berkeley Lab and Dr. Ayala Teitelboim, who was also at Lawrence Berkeley Lab at the time. They've developed some very sophisticated rate equation models that let them essentially calculate all the different, absorption and transition and energy transfer and luminescence mechanisms that are going on in these nanoparticles And from these calculations, they're able to actually model the ratios that we measure. So what you see here is the energy level diagram for erbium that I showed before. And I only showed energy levels up to a certain point because that's typically the range that's considered important for ratiometric thermometry. But in reality, there are a whole bunch of higher energy excited states, and at high excitation intensities, these higher energy excited states can actually become significantly populated. And so in their models, the collaborators account for a whole bunch of different higher energy excited states and transitions involving those states. And so the yellow boxes that you see in these two diagrams enclose the thermally coupled levels that give rise to the emission that we use to calculate the temperature dependent ratio. And then everything above that on the right-hand diagram is a higher energy excited state. And so again, through a detailed accounting of all the ways in which absorption, emission, energy transfer, non-radiative relaxation, and so on can occur, my collaborators are able to calculate the ratio as a function of excitation intensity. When they did that, they found surprisingly that their models actually predict that the ratio will increase with excitation intensity. The model values are just a bit lower than what we measure experimentally, but we don't expect an exact quantitative match since these models use many semi-empirical parameters. So what we can then do is to plot the relative increase in the modeled ratio values by normalizing those values with respect to their minimum. And we can then plot analogous experimental data. And what we see is that there's quite a good match between the measured and modeled relative increase in the ratio. And so again, I'll just emphasize that there are no free parameters that we use to get this match between the measured and modeled relative increase in this ratio. Finally, by looking at the modeling results in a bit more detail, we see that it's a combination of radiative and non-radiative relaxation from higher energy excited states in erbium that distorts the Boltzmann population distribution our ratiometric thermometry technique relies on and increases the ratio. And so, of course, it's important to be aware of this kind of non-thermal change on the ratio. But once we really understand this kind of effect in detail, we can calibrate it or work at low excitation intensities and still use this technique as a way to measure nanoscale hotspots. Lastly, just to really confirm that this effect was truly non-thermal, we did some final experiments where we coated some glass samples, substrates with a thin layer of platinum and then placed nanoparticles on these samples. The reason to do that is that the platinum, which is pretty absorptive in the near IR, will therefore absorb a decent amount of the laser light, but then we have this low thermal conductivity glass layer underneath that really is not a good heat dissipator. And so what that means is that we can get a temperature rise of hundreds of degrees when we shine a laser onto this type of sample. So what we did is we first started out by using just a plain glass sample, so no platinum on this one, and we measured the ratio as a function of excitation intensity, and unsurprisingly, we see an increase in the ratio, and that's this apparent self-heating effect that I just talked about. And then if we repeat this measurement with a nanoparticle on platinum-coated glass, then what happens is we get a much, much steeper increase in the ratio, indicative of true laser heating on top of this apparent self-heating effect. And we also lose the signal from the nanoparticle at certain points in terms of increasing the excitation intensity. And that's consistent with other reports in the literature that these nanoparticles degrade around 600 Kelvin or so. We then repeated this experiment for diamond substrates, which has a much, much higher thermal conductivity by orders of magnitude. And here we see that the results are the same, whether it's for a nanoparticle on bare glass, bare diamond, or platinum-coated diamond. And so that makes sense for a non-thermal effect, because in all those cases, there is no heating going on, and this increase in the ratio with excitation intensity is a purely non-thermal effect. Lastly, before wrapping up here, I just want to answer the question of how we're able to take a single one of these nanoparticles and place it at the exact location on the sample where we want to measure temperature. That's, of course, very critical, because if we don't have a way to do that, then this whole technique really falls apart. And so the approach that we take here is that we use an atomic force microscope tip, or AFM tip, to push individual nanoparticles around on substrates and place them at the location where we'd like to measure temperature. So the way that we do that, and a lot of this work right now is being done by my graduate student, Dinesh Pamiti, is that we essentially hack the nanolithography mode on our Park NX10 AFM, and then we use that to position individual nanoparticles on various solid substrates. And so the examples that I'll show here are for individual nanodiamonds that are about 100 nanometers or a bit less in diameter. But again, we apply this technique quite broadly to all kinds of nanoparticles. So we can do both microscale manipulation, which is how Dinesh made this R for Rochester that you see shown here. And then we can also do finer movements. So here's an example where we move one particle with respect to another by about 95 nanometers. And then here's another example of moving a single particle by just about 20 nanometers. And so this provides a powerful way to place single nanoparticles exactly where we want to perform our temperature measurements. So to wrap up, in my group, we really focus on pushing the boundaries of far-field optical nanothermometry. In the past, we've done a lot of work on using individual upconverting nanoparticles for sub-50 nanometer single-point thermometry. And that's really the majority of the work that I talked about today. And then we have some other projects in slightly different directions at the moment. Finally, I'd like to acknowledge past funding support from UC Berkeley and the NSF, the Molecular Foundry at Lawrence Berkeley Lab and Seagate, and then current funding support from the University of Rochester and the American Chemical Society Petroleum Research Fund. If you're interested in learning more, please feel free to visit our website listed here at the bottom of the slide. And then with that, I'd be happy to answer any questions.
Thank you, Andrea, for your informative presentation. We will now start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on that Ask a Question box located on the far left of your screen. We'll answer as many of your questions as we have time for. Now let's get started. Our first question, how do the upconverting nanoparticles compare to other fluorescent thermometers?
Sure. So that's a great question, because certainly these upconverting nanoparticles are not the only types of luminescent materials that have been used for thermometry. There's a lot of things like fluorescent dyes, proteins that have been used for thermometry, as well as other inorganic materials. So for example, nitrogen vacancy centers and nanodiamonds, and we work with some of these other materials as well. So I think some of the major advantages of the upconverting nanoparticles would be, first of all, they're just extremely uniform. And I talked about that a bit when I showed some of these ratiometric thermometry results for different individual particles. And you see that these calibration curves are really uniform from one particle to another. So that's a big advantage in terms of being able to do, say, a batch calibration where you calibrate a small number of single particles from a batch, and then you can go on and apply that calibration to a totally different nanoparticle from that same batch. So that's one big advantage. Another aspect that I'd highlight is because you excite these upconverting nanoparticles in the near IR, but then they emit hundreds of nanometers away in the visible wavelength range, that can be a big advantage if you're trying to avoid a spectral overlap with some other kind of signal. And that's such a huge anti-Stokes shift that you really don't get from a lot of other types of materials. And so that can be, a unique advantage as well.
Thank you for that, Andrea. So our next question, if you were to use a single upconverting nanoparticle as a thermometer in a plasmonic environment, such as the HAMR hard drive you mentioned, would you expect this plasmonic environment to change the ratiometric thermometry signal?
Sure. So yeah, that's an important question, right? Because we know that for something like that HAMR hard drive application, you're going to need to put these nanoparticles in a very intense plasmonic environment, and it's definitely reasonable to worry that, perhaps this plasmonic environment could change the temperature-dependent luminescence signal. And so one thing that's helpful is that there are other people who have already used these upconverting nanoparticles for thermometry in plasmonic environments. And they actually see that the ratio values that you get as a function of temperature are extremely similar to what you get in more of a conventional non-plasmonic environment. So that's kind of a helpful precedent there. You get some enhancement in the overall brightness, which is actually a big advantage perhaps, but you don't see distortions of the ratio. The other thing that can be helpful, and this goes back to what I was saying previously about having this advantage of a large separation between the excitation wavelengths and the emission wavelengths, and then also the fact that these wavelengths are just very tunable by changing these lanthanide dopants, is that you can basically ensure that your excitation wavelengths and your emission wavelengths are both not anywhere near the plasmonic resonance. And so that's something that we were thinking about when we selected the particular nanoparticles that we used for this work in order to try and avoid any interference with that plasmonic aspect of these HAMR drives.
Great, thank you. Looks like we have time for one more question. What are some potential ways to mitigate the non-thermal excitation intensity artifacts that you discussed, and what are the broader implications of this type of artifact?
Sure. Right. So as I talked about during the presentation, these excitation intensity artifacts, if you're not aware of them, can potentially really distort your temperature measurements, which is, of course, not ideal. So I think there are a few ways that you can get around it. So one is just to work at a fixed excitation intensity, right? So if you can stay at a stable excitation intensity value throughout your measurements, then you're not going to have to worry about these kinds of effects showing up. Kind of similar idea is to work at low excitation intensities, where even there, small changes in the excitation intensity will not give you this big apparent temperature change. So that's another way to avoid these effects. But then even if you're in a situation where you need to work at higher excitation intensities, and perhaps you cannot guarantee that the excitation intensity is held constant, just being aware of these effects, you can calibrate them by doing the excitation intensity sweeps that we did, and then take that into account so that you understand what is really a temperature change and what is this kind of non-thermal artifact. So in terms of, broader implications, I think that it's something to consider in the context of luminescence, nanothermometry more broadly, which, as I mentioned a few minutes ago, a lot of people are using with many different materials, which is great. Certainly, I think it's a really powerful technique. At the same time, it's important to be aware that many of these signals that have been identified as temperature dependent can also change due to other parameters, whether it's something like excitation intensity or, things like pressure, for example. There's a lot of reasons these signals can change. And so I think just doing these very careful experiments to really tease out what are temperature changes, what is something else, is probably important more broadly for the field of fluorescence thermometry.
Great. Thank you again, Andrea, for your time today and your important research. We'd also like to thank LabRoots and our sponsor, Andor, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Any questions we do not have time for today and those submitted during the on-demand period will be addressed by the speaker via the contact information you provided at the time of registration. This webcast can be viewed on demand. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues and anyone who has missed today's live event. Until next time, goodbye.